In this video, we're going to talk about clustering. We'll begin with a brief introduction and then talk about the k-means algorithm. Clustering is a modeling task if the response y is unobserved and categorical. It's an example of an unsupervised learning problem. There's no y column in the dataset at all. The unobserved y values are often called labels, and so the data is said to be unlabeled. Nevertheless, collections of the observations with the same label are called clusters. So essentially, we'll be able to divide our data set into different observations that together form clusters. In reality, clusters typically correspond to something like distinct subpopulations, and the data that you observe is a mixture of those subpopulations in unknown quantities. For example, 25% of your data could come from subpopulation A and 75% from subpopulation B. Worse, the number of subpopulations is almost always unknown. So this is another challenge of the clustering problem. As you can probably tell, clustering is a good deal more challenging than regression or classification. Nevertheless, the goal is roughly the same. Using the data, determine some function of the predictor that assigns an input x into one of the clusters. The data looks like this, so just like before, we have a bunch of x's. The difference now is that we don't have y's. For example, we could have the height and weight and thickness of some monetary note. For example, if we were trying to determine whether or not there are different kinds of banknotes that we see, to determine maybe if there's systematic differences in their manufacturing, or maybe if some are counterfeit, we would want to take several measurements on many different notes and then try to determine if those notes are systematically similar in ways or if there are notes that are systematically different. In the example of water, we could take various kinds of measurements of the water, pH, conductivity, dissolved oxygen content, and so on, with the goal of determining if certain observations are systematically different than other ones, because that may alert us to something like a water facility malfunctioning. Recall that in classification, when we had two predictor variables in one response, the picture often looked like this. We would have a scatter plot, and we would color each of the points according to the label that was given. The classifier that we generated looked something like this. In clustering, we get the same kind of scatter plot, but now none of the points have colors to them. Nevertheless, the basic idea is still the same. The clustering algorithm is going to ask us to color the points in some meaningful way. And in fact, the result of the algorithm would actually give us an entire rule, which would allow us to decide for any point in the feature space what that point should be labeled. Of course, in practice, we hope that our dataset actually looks something more like this, where the clusters are very clearly described, and that way we can model them better. On to the k-means algorithm. The k-means algorithm is a standard go-to algorithm for breaking a dataset into k different clusters. The algorithm has been around at this point for decades, and it has many variants. In general, the input is the same. There's a dataset that you're inputting and some number of clusters k. You almost never know the number of clusters in advance, and that's one of the challenges of the problem. The great part about the k-means algorithm is it's very simple. It essentially consists of 3 steps. First, you'll randomly guess the cluster centers, okay? And you'll hear different terms here. So some people will call them centers, some people call them centroids, and some people just call them means. It depends on how you're actually thinking probabilistically about the model itself. Right now, we're just going to abstract all of that away and talk about the algorithm itself as it's classically described. The notation that we'll use is CK. That's going to be the kth center. So there will be capital K of them, and we'll use lowercase k to index them. So they'll be denoted C1, C2, all the way up to CK. And to initialize those, we're going to initialize those to random points in the data set. Of course, we won't select the same point 2 times. So we'll have k different clusters, capital K different clusters, and those will be kx's that are randomly sampled from the data set without replacement. The next step is that we're going to assign each observation in the data set to the nearest center that we've generated. So now in our minds, we have k points from the data set, and we're just going to go through the rest of our data set, and we're going to pick every single point and associate it with one of those original k points that we sampled. And that's going to be our first guess at the clusters. Then what we're going to do is we're going to look at every single cluster that we've described, and we're going to compute the mean of the x values in that cluster. We're going to use that to redefine what the means were. So initially they were just randomly selected. Then we went to all of the points in the data set and we associated it with a center. And now we're going to redefine those centers to be the averages of the clusters. Lastly, we're just going to repeat steps 1 and 2 until nothing changes. If that sounds complicated at this point, just follow through the example. It's actually quite simple. So this is a one-dimensional example. We have 10 observations, and this is what they look like. I'll encourage you to think for a moment, if you had to label these into different clusters, we will use 3 clusters, how would you actually cluster these points? Okay, let's look at how k-means does it. K-means will start by randomly guessing the cluster centers. So I'll randomly select 3 points. These are the ones that I select, x7, x8, and x9. Then I'll assign to every single observation the nearest cluster. So this simply means that I'm going to color all of the points according to each of the colored centers that I've described. So all the points to the left of C1 all are green. X8 and X9 get assigned C2 because they're closest to C2. And then X10 gets assigned C3 because it's closest to C3. Next, we're going to redefine those centers according to the averages of the greens, the purples, and the yellows. And notice that those averages are going to move a lot. So for example, when I average the green center moves quite a bit. The purple center only moves a little bit, and the yellow center doesn't move at all because there's only 1 point in it. That's the first iteration of the k-means algorithm. From there, we're going to just repeat that process over and over and over again until nothing happens. So here are my same points. The next step of this says that I reassign the points. So when I reassign the points, notice that x7 changes. It was formerly green, but now the green mean has moved so far away that it actually gets relabeled as purple. So now when I average the points again, now the purple mean moves to incorporate that x7, and the green mean moves as well because it no longer has that x7 influence pulling from the right. I relabel points, and now when I relabel points, x6 goes purple on me. When x6 goes purple, again, the green and purple move left, and notice that C3, the yellow mean, is still sitting where it is because no points have changed that influence it. This shift in means causes a shift in points as well, so now x5 turns purple, but notice now after x5 turns purple, or at the same time I should say, x9 turns yellow. So now the purple mean has moved far enough to the left that x9 is actually closer to C3 than it is to C2. So it goes yellow, and as a consequence, on the next move, C3 is going to start moving. But not only does C3 move, but C1 and C2 also move because X5 was also reclassified. This change now also sucks in X8 to be yellow, and things keep shifting to the left. So now the means purple and yellow have now both moved to the left. We do it again, and now we notice that no points are relabeled. So every point is kind of statically closest to its mean. Since there's no reassignments, we declare the k-means algorithm done, and we've clustered our data set. So if we look at the top left and the bottom right, we notice that we started with points that were totally unlabeled, and now we arrive at these clusters that are derived from this kind of similarity measure that the k-means algorithm is using. Now this is the k-means algorithm in 1 dimension. You can of course use the k-means algorithm in any number of dimensions. You just have to have a distance function that generalizes to any number of dimensions. And the standard Euclidean distance does that. For example, here's the k-means algorithm in 2 dimensions with 5 underlying clusters where the k, the number of clusters, has been selected at the beginning to be the right number. K is equal to 5, and in fact the right number of clusters equals 5. Notice that over here in the beginning, since the points were randomly set up, we have these clusters that are clearly wrong. One of the clusters, this blue up here, is very, very small. The red is obviously way too large, and so on. But as we go through the algorithm, moving left to right, this is the iterations, we're moving closer and closer into a configuration of the clusters that makes a lot more sense. So by the time we get to the second row, the algorithm is already beginning to stabilize quickly, and by the time we're at the 9th iteration, we're essentially there. So now the question is, how do you choose k? How do you choose that number of clusters at the very beginning if you don't know what it is? To get at this question, it helps to think about how we can assess the clustering quantitatively. In regression, we had the residual sums of squares, and in classification, we had things like the accuracy. So the question is, what's the similar thing for unsupervised learning problems? For clustering in the k-means algorithm, the badness that we're looking at is the sum of distances to the assigned cluster centers. So you go to every point, you look at the cluster center that it's been assigned to, you look at the distance between those two, and then you add that up for every single point in the data set. We'll refer to this as the TWSS, or the total within sum of squares, because we're only looking within those individual clusters. Now, one basic way that k can be selected is through what's called an elbow or a scree plot. It plots the badness of the clustering algorithm against k itself, and we prefer k's where the badness levels off. So for example, a scree plot will often look like this, We have the number of clusters on the x-axis, we have the total within sum of squares on the y-axis, and these plots characteristically take a shape that looks like this. There's a steep downward angle, followed by a relatively flat downward angle, and the point right in the middle is referred to as the elbow. That's essentially a paradigm shift between the number of clusters and the kind of fit that we're getting from this algorithm. It's saying that effectively there's some diminishing returns that's coming from adding more and more clusters. And when you go beyond that point, you really hit very serious diminishing returns. So k is usually assigned to be that elbow point. Now there are other noteworthy points of the k-means algorithm that you should know about. First, different initial assignments may result in different clusters. So a good idea is to try several at the beginning. Run the algorithm over and over and see if you get relatively stable clusters. Next, k-mean can be modified for categorical data. So at this point, we've only seen it for continuous data, but it can actually be modified, and that's in many of the implementations. Next, k-means may be applied to segment continuous distributions in a useful way. So you may think that k-means is only going to be applied to situations where there are very distinct subpopulations. But in fact, even when we think that there's a homogeneous population, we may use k-means just to come up with an effective way to break apart the population into different chunks. Lastly, k-means is used all over the place. It's used to determine subpopulations for different genetic diseases on one side, and on the other side it's used to break up different pictures into different colors. So it can really be used all over the place. Lastly, I want to show you what happens when you select k's at different levels. So here's a clustering problem where you have exactly the same data set and you're running k-means on it for different levels of k. Notice here in the top left that when you say k equals 2, you're just breaking it into two chunks. Now that may actually be a somewhat useful classifier. It's doing something like this, roughly speaking, which may be useful, but it's clearly underfitting the data. There's much more structure there than the algorithm has found, and that's what's going to happen when k is too small. So for example, when k equals 3, we're getting a boundary that looks something like this. When k equals 4, it looks like this. When k equals 5, obviously you see it's looking this kind of correct pentagonal breakdown. And then when k equals 6, now it has to actually start subdividing real clusters. So you see things like this, or in 7, things like this. That is very, very common. Whatever k you actually put in, it has to find that many clusters. When you're able to see your data, it's very easy to determine when this is happening. The challenge comes when you're in a high dimensional space and it's hard to see your data. Doing k-means in R is very easy. If your data set looks like this with just x1 and x2, the built-in function k-means is going to run the k-means algorithm on your data set. You need to tell it the number of centers, that's your capital K, and then when you get that back, you can use the $sign to extract the centers that it found. Those are the C's that it has determined at the very end of the algorithm. If you had typed in $cluster, you actually get the class labels themselves. So you could use mutate, of course, to add this to your data set and then make a nice plot.